on load sequencing in pipe stress analysis. To make sure all of you are connected well, can hear me properly, can view my slide, I'll send out a pulse check to all of you. Please respond to it so that I know all of you are able to hear me as well as watch my screen, my PowerPoint. So please answer this pulse check. Thank you. I'll give you 5 more seconds for this. Okay, so I can see some of you answering the pulse check. Oh, okay. 30% of you already. 50% all of you say good, good, very good. Okay, thanks. Okay, so before I start this presentation on importance of load sequencing in pipe stress analysis, I would like you to participate in 2 polls. Okay, so how many of you here attending this presentation are existing AutoPIPE user? Doesn't matter if you also use a competitor software. This is a multiple answer poll, so please respond to this poll. I'll give you 10 seconds for this. You can answer multiple answer also. Doesn't matter even if you use old versions out of select of AutoPIPE. Okay, so I just want to see how many of these attendees here are existing users of Bentley AutoPIPE. 5 more seconds. Okay, so hope you selected the answer and hit the submit button on the screen. Okay, now let's see the result. So as I expect, 44% of you say yes, you are a user of AutoPIPE, 22% say other softwares, and 33% are not using any pipe stress software. Okay, thank you for joining this poll. And out of this 44% of the attendees here, how many of you have used the nonlinear load sequencing feature in AutoPIPE? Okay, so please respond to this poll. Of course, this poll is for the AutoPIPE users, that is 44% of the attendees here. So please respond to this poll so that I know how many of you are already aware of this feature. Okay, I'll give you 5 more seconds for this. So please answer this poll. Okay, thank you. Let's see the results. Okay, so majority of you, 62% of you say no. Okay, so I hope this presentation will help you to understand this very important feature of AutoPIPE. In fact, it's a unique feature of AutoPIPE. Okay, so before I start, let's see the major customer list of AutoPIPE. Almost all the multinational EPCs, owner-operators, you can see, are users of AutoPIPE. In the middle, I put in the recent win, Tenaga National Berhad. That's a power owner-operator in Malaysia. Petronas also started using AutoPIPE now in Malaysia, and Pertamina in Indonesia, PTT in Thailand. So all these are Southeast Asian users. Okay, so the agenda for today's presentation is approximately 40 minutes. So first we'll look into what is load sequencing and why it is important in pipe stress analysis. We go through 2 examples to explain this load sequencing, and then followed by explanation of multiple analysis set with the example 3. And then we summarize and open up for a poll and question and answer session again. So what is load sequencing and why it is so important in pipe stress analysis specifically? In a nonlinear analysis, the sequence of the load is important. Before we go into details, let's first ask ourselves, what is the need of a nonlinear analysis? Almost all the piping supports have either friction or gaps or soil support, isn't it? One of these 3, friction, gap, or soil springs. So if your model has any one of these three, then you have to do nonlinear analysis. That is a must. If you do not do nonlinear analysis, then the friction or gaps or soil springs will be simply ignored, leading to wrong results. That's why nonlinear analysis is very important in piping. Okay, and when you do this nonlinear analysis, the sequence of the load is important. On the right side, you can see 4 pictures. The first picture is self-explanatory, the apple dropping on a person's head. That's where the gravity was invented. So the first load is the gravity load. When we finish constructing a plant, constructing the piping, the piping will undergo small displacement, fraction of a millimeter or so, due to gravity load. That's what the first picture explains on the right side. And then once you finish the construction, once you start operating the plant, the temperature inside the pipe, because of the fluid, increases due to the operation of the plant. And that's the second picture shows you the temperature increase. And then the pressure builds up, or maybe the other way. First the pressure builds up and then the temperature increases because of the pressure buildup. So that's a sequence, isn't it? And the fourth one is the occasional load, such as wave, wind, earthquake, any one of this or a combination of all this. So these all happens in sequence, isn't it? First, the piping is subjected to gravity load, which undergoes deflection downward. And then due to temperature, it may undergo deflection again, but may not be in the same direction of gravity load, maybe in the opposite direction of gravity load. We don't know, okay? But the important thing is that the gravity load is analyzed with no initial state, and thermal load cases are analyzed with gravity as the initial load case. Okay, not as no initial state like our comparator. The thermal loads are analyzed with gravity as the initial load case. And then pressure load cases are analyzed with the corresponding thermal load case as the initial load case. Or it could be vice versa. That means thermal load may act after the pressure load. So we can tweak the program to do all those stuff. And then finally, occasional load cases are analyzed with gravity as the initial load case. This is not in agreement with the picture on the right side, isn't it? In the picture on the right side, the occasional load, such as wave, wind, earthquake, happens during the operation of the plant or during the shutdown of the plant, isn't it? So the default load sequencing, as explained in this slide, the bottommost sentence, occasional load cases are analyzed with gravity as the initial load case is the default. But that may not create the worst case, isn't it? Occasional load acting during the operation of the plant may be a worst case. That's what the pictures on the right side explains. So AutoPIPE's load sequencing, nonlinear load sequencing features allows you to sequence the load the way the user wants. And you can create multiple scenarios to analyze and design your piping model for the worst case scenario. So I hope with this slide, you understand what is load sequencing. Okay, so AutoPIPE's nonlinear load sequencing analysis is a advanced nonlinear analysis engine from Professor Emeritus from UC Berkeley for friction-gapped pipe supports and soil. Real-world load sequencing and path-dependent friction for accurate nonlinear results. Example, gravity, then pressure, then temperature, then seismic. Apply nonlinear gaps and friction to any load case. Building codes like UBC, which is followed by the structural engineers, must design with no friction in seismic load cases. And you see the AutoPIPE's loading time sequence. Gravity, then pressure, then temperature, then earthquake. This is the sequence. Whereas competitor software used one lump load vector, algebraically adding or subtracting all the load cases. time-dependent load sequencing is not a new concept. It's been around for many years in general-purpose finite element analysis programs like Abacus, ANSYS, and other high-end finite element analysis programs. Okay. Then we'll try to see why it is important. Let's go to this ASME Press publishing in 2009. ASME published this book called Pipe Stress Engineering book by L.C. Peng and Alvin Peng. So this book, in their section 6.3, mentioned that the analysis method used by many pipe stress software was incorrect, and that the only valid method was used by programs like AutoPIPE. Of course, this book won't mention any software name. They just mention the methods used by commercially available pipe stress analysis program. So this talk about these three sections, three methods in section 6.3 of their book, Pipe Stress Engineering by ASME Press, Peng and Peng. So three main approaches have been adopted by computer software packages in dealing with systems like the one shown in figure 6.8 on the right side, where we have the piping connecting two pressure vessels through the nozzle at both the ends. And on the right side, you see the tower, the pressure vessel tower, moves up due to the operation load, due to the temperature load. And because of this pressure vessel moves up, the piping that is connected to it also moves up. And by the way, losing the support number 20 first, and then later support number 30. Because of this, the effective length of this piping increases. Previously, in the cold condition, the effective length was only 5.2. But later, after support number 20 liftoff, the effective length is increased to 7 plus 5, 12.2 meter. And then later, even more. So this changes the condition of the piping, particularly the sustained stress. So let's come back to these three main approaches. Okay, the first method is called general straightforward approach. This is an approach commonly adopted by general purpose finite element analysis program, not special purpose pipe stress analysis program. The second method, as per the book, is algebraic subtraction approach. The third method is operation condition approach. So the book mentions only the methods, and the book don't mention anything about the software names. Okay, and the second method is adopted by a competitor program, and the third method is what AutoPIPE uses. Okay, so now we'll see in detail about these three methods. The first method is used by our finite element analysis programs like ANSYS, Abacus, etc. This approach mishandles both sustained and expansion stresses by taking in isolation. Only cold sustained stress considered, hot sustained would be higher, which is not considered. Expansion does not consider the restraining effect of the weight of the piping. So the expansion stress is underestimated. So that is the drawback of method number one, straightforward approach. The second approach is algebraic subtraction method, which our competitor use. This method has three major issues. Number one is the sustained stress is calculated at ambient condition and not at hot condition. So the sustained stress is underestimated. That's problem number one. Problem number two is by subtracting cold sustained from operating load includes cyclic weight range in expansion stress, not consistent with keeping primary and secondary loads separate as per the code. That's the second problem. The third problem is the temperature plus weight condition depends on sign of moments. If opposite, the combined result could be smaller than the expansion alone. So should consider absolutely to account for the reversing of stress as relaxation and cool down. Because the signs of expansion stress and sustained stress are immaterial, the algebraic summation or subtraction is meaningless. So that's why the book says this method also has 3 flaws. And they also mention about the third method, operation condition approach, which AutoPIPE uses. Here, the sustained stresses and expansion stresses are treated separately. Sustained stress is calculated under hot condition, capturing the critical sustained stress. So the authors only recommend the third method, that is the operation condition method, which is used in our AutoPIPE because it meets the code philosophy and requirements. The other 2 methods have flaws. This is what the book concludes in section 6.3 in their book. So from the above discussion, it is obvious that the operation condition approach is the only method that meets the code philosophy and requirements. The other 2 approaches have flaws in calculating the sustained stress and the expansion stress range. Operation condition approach like AutoPIPE is the recommended approach. To have a detailed look on this recommendation from this book, I would suggest you to go through this book, particularly section 6.3, that explains in detail about these 3 methods. Now we'll go through examples to explain this. The first example, I'm going to use load sequencing equal to operation condition 1 for occasional load case like seismic, wind, user, etc. So my example 1 has occasional load only seismic. I didn't consider wind for simplicity's sake. So the load cases are gravity, temperature, pressure, and seismic. And the seismic load follows the operating load, such as gravity, temperature, pressure. Okay, so OP1 is the hot operating condition, gravity first load case, temperature second load case. Since no pressure, so occasional load E1, earthquake 1, is applied in the hot condition after gravity and temperature are applied. And we also create a user combination in this example, that is gravity plus earthquake 1. This is to illustrate how this combination is inconsistent with the load sequence, because this is what the competitor does. Okay, so in this example, I'm going to consider this simple 3-leg piping having 6 points, A00, A01, A02, A03, A04, A05, with 2 bends, 1 guide support, and 1 V-stop support. I'm going to follow the ASME B31.1 2018 code. The pipe size is 200 mm standard pipe of A106 grade B material. Pressure is 0. Temperature is 280 degrees Celsius. And the earthquake is 0.6 G. Just 1 earthquake load in the positive Z direction. The bottom left side shows the axis orientation, global axis orientation in AutoPIPE. On the right side, you see the isometric view of this piping with the dimensions on it. So you get an idea about the spans. And in the middle, you see the user-friendly spreadsheet. This is why many of piping engineers prefer to use AutoPIPE, because it's so user-friendly to view the graphics together with the spreadsheet for editing simultaneously in one screen. This slide shows the plan view, the top view of the same example 1 piping model. And you see this the guide support has gap of 5 mm on the left and right. That is in the Z direction, the global Z direction, which you can watch in the bottom left of the screen. The vertical direction perpendicular to the screen has 0 gap. Only the lateral direction parallel to the global Z axis has 5 mm gap on both the sides. And the loads that we are going to consider are these 3 loads: gravity, temperature, and earthquake. No pressure load because pressure is 0. And we are going to follow that in this sequence, 1, 2, 3, gravity, temperature, earthquake. Okay, first of all, what are the commands that we need to use it in AutoPIPE to trigger this nonlinear load sequencing? The first thing is the static analysis load cases dialog, which I'll show you how to invoke this later in a video. So here you can see we use this dialog to select the load cases that you want to include in the analysis. So I have selected gravity, temperature, earthquake. And then I have selected at the bottom the gap/friction/soil. I put in a tick mark there. By putting in a tick mark here, the program will automatically invoke a non-linear analysis. If you don't put a tick mark here, and if you hit the OK button, the program will give you a warning that the gaps, friction, or soil in your model will be ignored, leading to wrong analysis results. Okay, so that will remind you to put a tick mark on this button if your model has one of this. So once you put in this tick mark and hit the OK button, then the right side dialog appears. This is the non-linear dialog. So here you can see this is useful for sequencing the loads. So you can see there's a tick mark for use default sequence. And then initial at the bottom, you can see initial case for occasional loads is operating 1. By default, this is gravity. I'll change it to operating 1 to have the sequence of first gravity, next temperature, next earthquake. That is what I'm simulating through this dialog. Okay, and then we look at the results. What you see, the deflection diagram on the top view, and on the bottom left, I have put in the cross-section of the guide support. So, and the load case considered here is the gravity temperature load, okay, in sequence. Load number 1 is gravity, which has 0 deflection. And you see the dotted line cross-section of the support. The pipe is at the middle of the support. And then when we go to the second load case in sequence, gravity to temperature, the pipe expands due to the 280 degrees Celsius temperature. And then the gap is closed due to the 5 millimeter movement of the pipe in negative global Z direction. That's what I captured in the cross-section of this support. And the gap is closed, and hence the support reaction is generated, which is 1025 Newton. Okay? So this is the movement of the pipe due to the hot condition, hot operating condition. And then we sequence the earthquake load as the third load. And then the pipe moves back in the reverse direction, in the positive Z direction of 7.75 millimeter. Still, it has not closed the gap on the other side. So effectively, from the middle of the support, the pipe moved 2.7 millimeter only. And we still have 2.25 millimeter gap on the other side of the support, in the positive Z direction. So the gap is not closed. Okay, so hence the force generated is 0. Okay, so there are 3 load cases involved in this slide: gravity, which has 0 deflection in the Z direction, and then hot condition, that is temperature load, which has -5 mm in the negative Z direction. And then from that position, the pipe moves 7.7 mm in the opposite direction due to the earthquake load. That is the third load case, hot plus seismic in sequence. So you can see point number A05, G2, due to the gravity, temperature, earthquake load, it moves 2.75 millimeter at the end, but it undergoes 7.75 millimeter from the hot position. That is the second load case. Okay, so that effectively the gap is not closed and no force is generated at the support. Okay, so hope this slide is clear. And let's see the results in the output file, particularly the default non-code combination, that is gravity, temperature, earthquake. is consistent with the load sequence. So the deformation is 2.75 meter, which I highlight, 2.75 millimeter, which I highlighted on the screen, the bottom right side in the Z direction. And I also create a user combination, which is inconsistent, that is gravity earthquake, which produces 7.75 millimeter in the global Z direction, which is exceeding the gap of 5 millimeter. And see the force generated 1025, which is also inconsistent. That's why we call it as inconsistent user combination. Okay, so next we see the analysis summary that explains the basic load cases for nonlinear analysis as gravity having the initial load case as none, and then temperature having the initial load case as gravity, and then earthquake having the initial load case as temperature. So the actual load sequence is gravity first, then temperature, then earthquake. Okay. So all these things which I explained now, I'm going to show you in a video, a 5 minutes video, so that you can clearly understand the steps involved in achieving this nonlinear load sequencing for operation condition. Just give a few seconds. Okay, the video is getting loaded now. Okay, so now you can see the isometric view of this 3-leg piping. And the gap support has 5 mm gaps in left and right, the lateral directions. And there is a V-stop support having support only at the bottom and not at the top. Okay, so first we'll see the load cases involved in this model. There's 4 simple load case: gravity, temperature, pressure, and earthquake. And we can ignore the pressure because it's 0 Newton per millimeter square, and the temperature is 280 degrees Celsius. Okay, so now we look at the top view. I'll unselect the selections, and then we go through the we switch off the lens, and then we go through the static analysis sets. So there is only, before that we go through this earthquake load also. There's 0.6 G in the Z direction, global Z direction. And then we go through the analysis sets, static analysis set, and you can see that the load cases considered are gravity, temperature, and earthquake. And when I click on modify button, here you get this static analysis load cases dialog, where I click on this gaps, friction, soils option, and then press the OK button, which triggers the nonlinear analysis. And at the bottom, I change the initial load case for occasional loads from gravity to operating. That's it. We now achieved the nonlinear load sequencing, and we sequence the load as operation condition, meaning the occasional load cases will be applied after the operating loads are applied. And then we capture the sequence and the displacement and stresses in a correct state. Okay, so now you can see this dialog shows the nonlinear option is selected. Now we look into the displacement diagram. First, due to thermal, and here you can select A04. And you can see, due to this thermal load case, the displacement is 5 mm in the negative direction, and due to the static seismic, it's 7.75 mm in the positive Z direction. And the next load case is the sequence: gravity, then temperature is -5 mm. And next is gravity, temperature, earthquake sequence, which is 2.75 mm. Okay. So let's go back to the gravity, temperature load case, which is -5 mm. The gap is closed. We go back to our PowerPoint and explain the same thing in the slide, which is -5 mm gap is closed and the support getting reaction. And then the next final load sequence is gravity, temperature, earthquake, where the gap is not closed, which is 2.75 mm deflection from the center. That is effectively 7.75 mm from the left side of the support. Okay, so due to this sequence, the gap is not closed. due to gravity, temperature, earthquake combination, or the sequence to be more exact. And see this user-defined combination of gravity, earthquake, which is producing 7.75 mm deflection in the positive Z direction, which is impossible. That we can capture through this load combination dialog, which highlights this load case as blue color, meaning inconsistent combination because of load sequencing. The reason why I'm showing this is because this is what the competitor program does. Since they do not have the load sequencing feature, they algebraically sum up the loads, which is not good for a nonlinear analysis, producing wrong results. So the correct result is 2.75 mm. Wrong result is 7.75 mm. So competitor program gives you reaction for this gravity, temperature, earthquake combination, whereas AutoPIPE will not give you the reaction because support is not closed. So that's what we learned in example number 1. So now we'll move to example number 2, where I use the same example, and instead of operating load condition as the initial load case for my occasional load, I use gravity as the initial load case for my occasional load. So gravity is the cold operating condition, and then the occasional load earthquake uses this as the initial load case. In the previous example, the earthquake load was using the operating condition as the initial load case. But now, in this example too, we are using the gravity as the initial load case. And since no pressure analysis, so case E1 is applied in the cold condition after gravity. This is also possible in the site, isn't it? The earthquake may happen during the shutdown of the plant, or we may shut down the plant due to earthquake or due to high wind load, like typhoon or storms, isn't it? So that may be a worst case. We don't know. Okay. So example 2 tries to capture that effect. So how do we do that? Okay. The same dialog. On the left, we select the gaps friction soil button to trigger the nonlinear analysis. And on the right dialog, we select the initial load case for occasional load as gravity. And then the results are captured here. You can see here the load case is GE1, and the deflection is 5 mm in the positive Z direction. Okay, closing the support and giving support reaction. And we also captured these results in the output file, and we can see this default load combination is consistent with the load sequence G1 bracket 1, and that is even the non-consistent user-defined combination gives the same result in this case. Okay, and the analysis summary, we captured the load sequencing as gravity uses no initial state, temperature 1 uses gravity as initial load case, earthquake load uses gravity as initial load case. So the actual load sequence is gravity first, then temperature, and another load case, gravity first and earthquake next. Okay, so we go through the steps in a 2 minutes video. Again, the same small example, we use it to demonstrate this. Only change that we are going to do now is go and modify this example 1 and change this load sequence from operating load case to gravity load case for the occasional load. That's it. And our example 2 is ready. We converted the example 1 into example 2 and reanalyze the model and capture the displacement due to GT1, which at point A04 is minus 5 mm, and then GE1, which is positive 5 mm. So both the load cases, the support is getting closed, and you get a reaction for both the load conditions, both the load combination. Okay, we should not look into the primary load cases such as temperature load case or earthquake load case because they are not consistent with the load sequencing. So let's go through the output file. And we look at the support forces for A04 support, A04 joint. Particularly, we are interested in GT1 and GE1, bracket 1. okay, 5 mm and minus 5 mm. And see the user combination GE1, which is producing the same result as the load sequence GE1 bracket 1. I'll explain about that bracket 1 little later. In third example, I'll explain that. Okay, and the analysis summary explains the sequence of load. Okay, earthquake load is applied after the gravity load, unlike the previous example where earthquake load is applied after the temperature load. So that's what we see in this example number 2. So let's summarize both the examples as case 1 and case 2 in this spreadsheet. Okay, and the small pictures on the right side explains you the movement of the pipe to the left and right of the pipe support. So first, let's consider the operating load case number 1 as initial state for earthquake 1, that is sequence A, gravity, the displacement is 0, the reaction is 0. The second case is earthquake during operation, that is sequence B, load is gravity plus temperature 1, and the displacement is minus 5 millimeter in the global Z direction, that is dz. The reaction is 1025 newtons. And then we go to sequence C, that is actual case, gravity, temperature, earthquake, all happens in sequence, that is C, gravity plus temperature plus earthquake, and the result is displacement 2.75 mm. It is not negative, it is positive 2.75. I apologize for this typo error. It is 2.75 millimeter in the positive direction. Still the support is not closed, so the reaction is 0. And then let's consider this user case E1 and GR plus E1. That is C minus B, where you get the E1 load, that is 7.75 mm, which is exceeding the gap of 5 mm and producing the reaction 1025, which is wrong. And we use this another case, A plus C minus B, that is to calculate obtained by superposition, gravity and earthquake load, which also produces 7.75 mm. And the reaction is also same as 1025 Newton, okay, which is also wrong. Okay, that's why the sequence C minus B and A plus C minus B, this is what the competitor program does. They just simply superimpose the results. And those results are not consistent with the sequence of the time of the application of the load, and hence producing inconsistent results. And the pictures on the right explains what is really happening. Okay, and the case number 2, using gravity as initial load case for earthquake 1, earthquake load during cold case, actual case, that is GE1. On the top, you see the gravity load produces 0 displacement for case 2 and 0 reaction. And for sequence B, gravity plus earthquake 1, it's minus 5 mm is 2013. Okay, the reaction is 2013. The gap closes, large reaction. I apologize again, this should not be minus 5, it is positive 5. Gap closes, large reaction, so small displacement and stress. Okay. So the bottom line is that when support conditions change, superposition leads to inconsistent and less accurate results. Okay, so do not use the load combinations in a non-linear analysis. Use load sequencing instead, as used by AutoPIPE. Okay, so the recommendations are, it is recommended to evaluate the maximum support loads and movements by analyzing both gravity and operating default sequence. Also, remember to include the positive and negative seismic and wind loadings for worst case evaluation of occasional loads and stresses. Okay, but remember, we achieved this operating condition as well as cold condition by using 2 examples. But why can't we do it in one single example? That's what example 3 does. By utilizing the multiple analysis sets feature of AutoPIPE. So using this multiple analysis set, we can perform multiple analysis in one model. Also, we can create multiple scenarios of load sequencing in one model itself. Just like example 1, which follows the operation condition approach, example 2, which follows the cold condition approach. Okay, that is gravity as initial load case for occasional load. That is example 2. Example 1 is the temperature as initial load case for occasional load. So let's see this through a video, multiple analysis sets video. So we use the same example 2 to demonstrate how we convert this into example 3 and achieve these 2 examples in one model. So first I open example 2 and save this file as example 3. Okay, and then we go to the static analysis sets in AutoPIPE, and we see that the initial state for occasional is gravity. We now change it to operating 1 as in example 1. And then we select this analysis set 1. We don't analyze it. Just reselect the analysis set 1 and then duplicate it as analysis set 2. But we go and modify the analysis set 2 as gravity, similar to example 2. So analysis set 1 is example 1. Analysis set 2 is example 2. Both examples in one single model, example 3. And we now analyze this multiple analysis sets in one single model, example 3. And we get the results of the worst case of both. So we see the bracket 1, meaning analysis set 1, and bracket 2 at the end of every load case, that is analysis set 2. So we now go through this GT1E1 bracket 1 and look at the deflection. And we look at the plan view, the top view, for the same node A04, and we notice the 2.75 mm in the positive Z direction, same like our example 1. And now we'll go to GT1 for analysis set 2, and we see the displacement is minus 5 mm, and then GE1 for analysis set 2, which is positive 5 mm. Okay, so this way we are capturing the sequence of load, the occurrence of the occasional load such as earthquake load, both in the operation condition of the plant as well as the shutdown condition of the plant, and let the program decide which is the worst case and design it, give you the code stress. And the load combinations highlighted in blue color are all inconsistent with the load sequencing. So we should not use those results. Okay, so you can see more in non-code combinations. We look at the output file, particularly the support forces and analysis summary. And we go through this support number A04 for support. That's where the guide support is located. And note that friction is not included in this support. We have only gaps. And see this static seismic as a primary load case, which is an inconsistent load case, showing 7.75 mm displacement, which is impossible because the support has only 5 mm gap. So we should rely on the results of consistent load sets like GT1, GT1E1, etc. And for the second analysis set, bracket 2, GT1 bracket 2, GE1 bracket 2, we see the supports are closed in both the directions and giving reactions in the support. And in the analysis summary, we see the static analysis set number 1 and the sequence for that. And then we see the static analysis set number 2 below. Okay, and the sequence for that. Notice the differences. The earthquake load is having gravity as initial load case in analysis set 2. And then we see the code compliance combinations On the right side, we see this D/A/P/C, and Y means yes, N means no. And here we see the nodes. D means default, A means auto update, P for print. We are more interested in the last one, that is C, meaning consistent. And we should use the results only for yes for consistent. And we should not use the results which says no for consistence. And the non-code combinations also same thing. We should not use the result of N, meaning no for consistent. But still the results are printed in the output file, even though it is not consistent, just to compare with competitor programs. Okay, and now we select this code compliance result also. And there you can see the ASME B31.1 code compliance. On the left side, we see the point name and the load combinations. And these are the code combinations which are consistent with the load sequence. And we see the moments, stresses, both the actual and code allowable. And make sure the code stresses are less than the allowable stress. And some locations we see the double asterisks, meaning the allowable stresses are exceeded by the code stress, the actual stress. But with the sustained load margin, you see the allowable stresses are increasing. So by default, AutoPIPE uses this sustained load margin. But if you don't want to use it, there is a configuration that you just need to change in AutoPIPE settings. Okay, and you finally see this result summary, maximum sustained stress ratio, and the maximum displacement stress ratio, the maximum occasional stress ratio, and the maximum hoop stress ratio. So you see the hoop stress is 0 because there's no pressure. So the governing case for this example is the displacement stress ratio, which is producing 0.94. Okay. So at the bottom of the output file, you can see the system satisfies the code. And finally, we look at this stress contour showing the stress ratio. And here we capture the maximum ratio as 0.94 due to the temperature range, expansion stress. The other sustained stress and occasional stresses and hoop stresses are all less, producing less utilization ratio. Okay, so with that, we explained the importance of the load sequencing and also the multiple analysis set. To summarize our presentation, ASME Press Pipe Stress Engineering book by L.C. Peng and Alvin Peng, published in 2009, mentions that the operation condition approach is the only method that satisfies the code philosophy. So please read the section C 6.3 of this book to have a detailed understanding about these methods explained in this book. And the book concludes that the other two methods have flaws in calculating the sustained stress and expansion stress range, which is used by the competitor program, a flawed method. The multiple analysis set feature in AutoPIPE helps in creating multiple scenarios of load sequencing in just one model. So I just used two scenarios to simulate two scenarios in one model, but you can simulate much more scenarios in one single model. For example, pressure before temperature. Okay, and pressure before temperature with operation load condition for the occasional load case, and then pressure before temperature with gravity load case for occasional load case. So like this, you can create multiple scenarios in one model, and then analyze for the worst case of all. So that brings to the end of my presentation. We have a Bentley Pipe Stress YouTube channel. Please subscribe to it. We have many videos getting posted there on the latest features of AutoPIPE. We also have all the trainings of AutoPIPE, all the training materials available for download and videos for on-demand training, all available in learn.bentley.com site. This is available for all our Bentley users under our select contract. Those who are having maintenance with Bentley can utilize this LAN server to get trained on our AutoPIPE programs free of cost and print the certificate signed by Global Bentley Institute lead. Support, there are several ways to reach out to our support team. The best way, easier way is to utilize our communities.bentley.coms. There you can utilize the forums, you can utilize the blogs, wikis, and examples to post your question, to see the questions posted by other users, and to see the answers to Google search your query of AutoPIPE that will lead to the community's posting. Or if your question is confidential, important, one-to-one support is what you require, then you can raise a service request manager by using this link. Or you can utilize the Connect Advisor. This opens up automatically whenever you launch Bentley AutoPIPE program that advises you on the latest videos and training materials and discussions happening in our community site, YouTube videos, and blogs, etc. Okay, so now that you have understand the importance of load sequencing in AutoPIPE, can you please help answer this poll to if you plan to use this feature in your upcoming project? This is not that easy topic to understand. The basic concepts are easy to understand, but the flaws, to understand the flaws in the other two methods, as discussed in the book, you just need to rewatch it again or read the book again. But this is very important for pipe stress engineers. So please help answer this poll. If you understand this importance of nonlinear load sequencing in AutoPIPE, do you plan to use this feature in your upcoming projects? I'll give you 5 more seconds for this. Okay, thanks for joining in this poll. Let's move on to this next poll. Okay, so this is the result of the poll. 96.4% of attendees here, or AutoPIPE users here attending this presentation say yes, that you understand this nonlinear load sequencing and you will use this feature in the upcoming projects. That's very good news. And that's the goal of this webinar, to reach out to you on the importance of this nonlinear load sequencing. Next poll is about our sales team to reach out to you. If you want one of us, the technical team or sales team, to contact you as an action item after this webinar, please utilize this dialog to answer this poll. I'll give you 5 more seconds to answer this poll. Okay, thank you for submitting this poll. Now let's move on to our question and answer session. At the bottom of your screen, you can see this question and answer box. So please utilize that to post your questions. Okay, there's a question about, can we do pipe stress analysis for buried underground pipes? Very good question. In fact, AutoPIPE strength lies there, buried piping. Why do I say it is AutoPIPE strength? Because buried piping requires you to model the soil spring supports. In competitor program, you have to split the buried piping into several segments to analyze your buried piping accurately, to calculate the soil springs accurately. But the advantage of AutoPIPE is that the user don't need to split the piping physically. The program will internally split the piping based on the user's configuration, the user's requirement. That way, the model you will handle through the graphical user interface have fewer nodes compared to the fewer points compared to the competitor program. So AutoPIPE is well known for buried pipes. Okay. Okay, another question is about gravity, temperature, pressure, earthquake, but slide shows gravity, pressure, temperature, earthquake. Doesn't matter, Kalpesh, because in this example, we didn't consider pressure. The pressure was 0. So whether temperature and pressure interchange produce the same result. And in fact, even if you have some value for pressure, the interchanges of pressure and temperature will not change the result significantly. Small changes in result will usually occur. But usually, the importance lies in how you sequence the occasional load, such as earthquake and wind load. And sequencing the pressure or temperature load, interchanging that doesn't really matter. That's what my experience is. Okay, another question. Can many different operating cases be used as the initial case in different analysis set? Definitely. That's why, remember, in my presentation, I used T1, temperature 1, earthquake 1, E1, pressure 1, P1. So you can use as many, if you use AutoPIPE advanced license, that give you more number of temperature load cases and pressure load cases. But if you use AutoPIPE basic license, it gives you 5 load cases for temperature load cases only. Okay, so but in any ways, to answer to your question, different operating cases such as temperature 1, temperature 2 can be used as initial load case in different analysis set. Yes, and that is one of the importance of multiple analysis set, which is helping this to create multiple analysis scenarios, multiple load sequence scenarios in one model. Okay, another question is how to check the hot sustained stress. Okay, AutoPIPE does calculate the sustained stress due to the hot condition, and you can view that in the output file GT1. Okay. In your presentation, you mentioned about hot sustain, how to consider for the hot sustained load case in analysis. Okay, this is what the same question as previously. AutoPIPE does consider the hot sustained load case as GT1. Okay. Okay, another question is, sorry, I missed that point. How did you consider both analysis set, cold/hot, in example 3? Okay, I'll explain it again. In example 3, remember, the purpose of example 3 is to simplify the model. Instead of splitting as example 1 and example 2 to simulate hot condition in example 1 and cold condition in example 2, in one single model in example 3. Okay, by just changing the initial load case for occasional load as operating load case in example 1, as gravity load case as example 2, and then using the multiple analysis sets in example 3 to simulate both cold and hot in one model. Okay, so that is what all this presentation is all about, sequencing the load case, considering the cold condition as well as the hot condition for your occasional load case, okay, to get the worst case scenario. Okay, So, okay, I think that's questions. I think almost all. Yeah, there's one more question. What is the support stiffness value of AutoPIPE compared to other software? Unless we change the default, the program gives you option to change the stiffness value. By default, it is rigid. Okay. And the directions of the support, there are plenty of support options available, varying from guide support, vertical stop support, line stop support, spring support, hanger support, incline support, friction support, link tiling supports. So many supports available in the software. So in fact, a simple guide support takes you at least 10 steps to model in competitor software. It just takes 2 steps to model it in AutoPIPE. Because of the restraint feature you follow in competitor software, AutoPIPE simplifies many things. So modeling in AutoPIPE is much easier, very important. The analysis results are more accurate in AutoPIPE. And the proof is the book. So if you're not read section 6.3 of the Pipe Stress Engineering by ASME Press by Peng and Peng, I would suggest you to do so to understand the importance of the operation condition approach as explained in the book. Okay, so with that, all the questions are being answered. If you have missed out some part of the presentations, if you have any audio or video problems during the presentation, I would suggest you to wait for the thank you email for joining this webinar and rewatch this webinar using the same link as it will be available on demand few hours after the end of this live presentation. So the next AutoPIPE webinar will be next month, approximately the first Wednesday of every month. We'll plan to do this AutoPIPE webinars. So please join us every month to learn more about our pipe stress analysis software, AutoPIPE. Thank you very much. So over to you, Tiam and Derek.
Yeah, thanks everyone for attending today's webinar. I'll be ending this webinar. If you have any questions, you can drop any email to Madan or Tiam after this webinar. Thank you, guys.